back for 15.2. Double integrals over more general regions. It more or less means any region, but not quite. It gets kind of complicated. It can be kind of complicated. But anyways, we'll see. It does get complicated, but you develop some skills, and yeah, I won't. Once again, I always say this, but it's true. I won't give you anything really hard to do. All right. Anyway, then, so like I said, 15.2. So. Double integrals over more complicated integration regions. Okay, in other words, not rectangles anymore. All right, that property of being rectangular really simplified things quite a bit. Again, if you remember, it made the two different integrals that we had to do independent of each other. So it's really quite a bit simpler. You're not restricted as much. But it's a very special case. So you need more complicated ones than that. So we'll look again some fairly general looking ones. It can get complicated. I keep saying that, but you won't have that much to do for these cases, right? So anyway, then we try to draw a little picture here without getting too out of hand. So now I'm going to show the three dimensions explicitly. Okay, so I'm still integrating. My region of integration is still going to be the XY plane. Okay, but now that'll be kind of down here horizontally. So I'll be drawing pictures kind of like I did last time of the region of integration. And then for here, the region of integration will lie in that plane, and then the function we're integrating will be of the form z is f of x and y. Okay? So anyway, it's kind of like this. Then let's say down here, I just got some region, and I want it to be pretty general. I'm not being specific about it at all, but it's just some region down there. I mean, this is this is finite. It doesn't have to be finite. There are such things as improper integrals. It doesn't have to be just one blob. It could be disconnected, possibly. But anyway, there's a kind of thing. So now let's just say we're in a, so I'm looking at a function. So say up here. We've got a function of the type that we've been playing with in 2.14, or chapter 14 rather. Okay, and so the idea is, here's the region in the plane. Well, up here on the surface, there it is again, and kind of think of it as a kind of a cylindrically shaped thing. Okay, so again, up here is the function z is f of x, y. There's my region D. This is the volume, okay, in this cone here is, say, a volume between the function z is f of x and y and the region D that I'm integrating over. All right? So in fact, here when I do this integral with that function, that's what the interpretation or an interpretation of this integral turns out to be under those circumstances. Okay. Once again, there's a better picture in the book. You can look at that stuff there. So, like I said, D is fairly general shape. In principle, it's not too hard to deal with generally. And it looks like that again, so there's our surface. Anyway, So again, the notation looks the same, really. I'll just go ahead and write it up here. So I'm integrating over a function. So again, that's just my notation for my integral I, f of xy, dA. Again, that's my area element. It would be the same kind of construction down there that I had before. Again, you can see something, a better picture of the book if you look. All right. Once again, geometrically, you do a Riemann sum here. I'm not going to try to draw that. Once again, it's in the book. You can go see that stuff. So once again, the geometry is pretty much the same. It just gives you this volume. And when we do the integrals, we'll be doing anti-differentiation again. Okay? Let me make a comment on something here. Okay. F of xy can be just about anything, right? Depending on what you're doing. A special case, a useful case, occurs if it happens to just be the number 1, right? The trivial constant function f of xy is 1. If you do that, then in that case, then this integral, again the double integral, f of xy dA, just gives us the volume, or the area of D, my bad. Okay. So in the special case, when f happens to just be the number 1, once again, then the value of the integral happens to be the area of that. We'll do an example of do the area of a circle a little bit later, just to see how that works. Okay? Anyway, there's still an area element like we did before. So again, if that's my, say there's x and there's my x plus delta x, just like I did last time. Okay. And out of those, like this, and I don't get too bogged down here, but works the same way. I integrate over a small area element dA. All right? And you can actually see from all this too that dA, and we saw this in the rectangle, so this isn't exactly new either, but really dA can be thought of as just the product of the two infinitesimal elements from ordinary integration theory. And at this point, there's, as we'll see, I'm not going to say anything about what order I'm doing them in here. That's something that, again, in the rectangular case, I could use any order I wanted. That was something there, it just didn't matter. Here, it's going to matter, but it's still going to be up to me to do. So this is the kind of skill you have to develop so that you can do these things. All right? Setting these things up. Right, and so just see how that works, because again, that's really where the tricks come in. Anyway, then, let's look at a special case, another special case, but one that comes out to be really useful. Okay, and that is the following. Again, very common, very useful. If we focus on particular types of integration regions, just written up here. There's two subcases here. They really work out about the same way. But anyway, what happened when they have a certain kind of geometric simplicity that I'll show you right now, and then they can either be horizontally or vertically simple, depending on how these things work. Okay, often actually, a lot of regions are both horizontally and vertically simple. And sometimes dealing with it one way versus the other can make a big difference in how hard you have to work. Anyway, it's pretty simple to see how it works though. So, for example, if my region of integration happens to look like this, and it's going to involve a couple functions, say. I'm just arbitrarily drawing these things here though, all right? So let's say that we're integrating again from, say, x from some point A, to the other limits B, all right? And then what I have here are two functions like that say give y as functions of x. And then let's say our integration region is this area here in between, well, in between A and B, and then also between those functions there, okay? So this is a situation that is referred to as being vertically simple. Okay, and all right, here's where we get the theory begins to come in now. When I'm integrating, what I'm going to do here for this vertically simple case is think about it this way, is that so for every value of x, there is going to be an integration interval that looks something like that, say whose bottom part is this function f1 and whose top part is this function f2. So again, when I integrate, I have to sum up all the values inside here of the function, and so that's exactly what I'll be doing for each value of x. I'll sum these guys, so each value of x, I will do a y integral that will say give me this length. Then, when all that's done, I'll in turn go back and integrate over x. And those two processes will cover the whole region. All right, and yeah, and there you go. So anyway, I'll just mention here, we'll do an example here in just a second. But anyway, just let me go ahead while I'm here and kind of point out that, well, if I could do that, then I should be able to kind of do the converse, all right? And so let's say, now the situation looks something like that. Okay, and so now, let's say I'm integrating over y from C to D. Now I have two functions here that give me, say, x. Use G, I'll use different letters here. Okay, so kind of like this. Sorry about that. Hang on. Let me redo that. Okay, so x is, say, g1 of y, and over here, x is g2 of y. All right, so again, for each value of y, just like I was saying here, I will integrate from g1 to g2. That'll give me that length, and then once again, I go back at the end of the day, and I integrate all these values of y from C to D. All right, well, if this one is vertically simple, then it's probably not a stretch to suggest that that one might be called horizontally simple. All right? So anyway, these are just two common types of geometrical situations that one encounters. This is the region. We call these regions D. It doesn't really matter. Anyway, so there certainly are shapes that are neither one of these. But like I said earlier, there are also many shapes that are both of these. And again, another thing that can happen too is if a region itself is not horizontally simple, it can often be decomposed into regions that are simple in this sense. So this doesn't necessarily do everything you need for these integrations, but it's quite a lot. If you can do these, for these two cases, then you're on the right track and you can figure out the rest of it. Okay. Once again, the book discusses all this. Okay. So let me just kind of develop that a little bit on the way to an example. Okay. So let's just focus on a vertical case for no particular reason. Okay, so same thing. There's my AB. Y is G1. And Y is G2. Alright, so my region is this strip in here again. Alright, and again, each point x, each value of x, and in that interval, I integrate from G1 to G2. Okay? So then, in our notations then, the double integral, in general, say it looks like this. Okay, so doesn't matter, call it I or something. Anyway, so there that is. Now, when I'm parameterized like this, it's pretty easy to write it down, so I'll just go ahead and do that. So my outer integral, the second one I do, will just be my x integral from a to b, right? And then the inner integral is the y integral, and its limits are these functions, okay? So that's the important part here. Notice, unlike the rectangular case, my limits for x are constant. That's where the simplicity actually means. But now, in order to do this, the limits of my y integral are functions of x. Okay? Anyway, so there you go. We're still integrating over general function f of x and y. Now, if I'm doing it like this vertically simple, everything I was just saying said that the y integral has to come first, right? Because again, that depends on x. So I got to get that out of the way, then I can do this one. So that means I have no choice in the order for this case. And I have to integrate over x first, okay? Or I'm sorry, over y first, my bad. So the idea is, using the terminology that we used last time, I will first do what I called last time the inner integral, like that, right? And when I do that, that's going to kill y. There will not be any y's left in here after I do this integral. I'll integrate y out. But it'll be a function that depends on x, because the limits, again, are functions that depend on x. So this is what I'm going to do. First, I will do the inner integral here, and kind of let the x integral sit there and wait for me, and then when I'm done, I'll come back and stick in the answer that I had, and then do the x integral, and I'll have it. Okay? So again, and when I'm doing that y integral inside here, this x is constant. It's regarded as being fixed. So again, think about that as we do the example. Okay? So, yeah, there you go. I'll just mention maybe in passing here that if I could do it this way, you could see that rather vertically simple gives me this construction, Well, the other thing we had, that horizontally simple picture, that'll just be the opposite, right? First I'll do the x integral, then I'll do the y integral, but logically it's really just about the same. Okay, good. Yeah, there's some regions can be done either way, some are a lot easier one way than the other. So anyway, let's just move on to some examples. And so let's start with this one, and I'm actually going to do the integral two ways to show you how. So let's get rid of that. So, and this is kind of typical. So let me go ahead and write this up here. Okay, so the problem here. So find the area, say, between the curves y is x squared and y is x plus 2. Okay? And I'll set it up both ways here, and I guess I did it both ways. We'll see what goes through that, but it can actually show you how that works. So anyway, you got to think about what that means. All right? Well, it's not hard, though. This, of course, is just a parabola, and that's just a straight line. So basically what you want to do is just find out how they sit. So you guys can do this. You know how to do it, so I won't really bore you with the details very much. But anyway, go ahead and see, so here's my parabola, say, y is x squared. And then the other part is a straight line that happens to look something like this. Okay? And this is my line, y is x plus 2. And you can invert these and write them the other way. You can, in fact, we'll do that here in this, yeah, hang on, we'll do that in just a second, I guess. Anyway, so it looks like that. You got to know what these points are, because that's going to be the limits of my integral. But you just get those by equating those lines, right? And you'll find out here, you guys can do this. That corresponds to the point x is minus 1. That's y is equal to 1. This one over here is x is 2. And that corresponds to the point y is 4. Okay? So there's the setup. And now I say the area between the curves. That means this is the area I'm looking for. All right? So now, like I said, we can do this in a couple ways. And yeah, it doesn't matter what order we do it in here. But anyway, so this is a shape that is both vertically and horizontally simple. Okay? And so say using the horizontally simple picture, that looks like that. Well, this is what it's called. And so that integral will be this one. Say x will go from minus 1 to 2. Right? And then, like I said, for each point, then, for a given x here, it's going to have to run from here to here. Right? And so that will go from, let me go ahead and get that written up here, okay? So that means y starts out at x squared, that's the bottom curve, and it will run up to x plus 2. That's the top curve. So there's the parameterization, all right? And again, doing it in this order, where x is the second integral, well, 2, and I'm finding the volume, or the area rather, So the function I'm integrating over is just the number 1. All right, and then so first I do the y integral, then I do the x integral. Okay, so there you go. So anyway, the first integral is easy to do because it's, you're just integrating 1. So let's see, the outer integral stays for a while, so x is minus 1 to 2. Then what I'll have here will be x plus 2 minus x squared, okay? Because that's basically that number minus that number. So that's the integral, that's the answer to the inner integral, okay? And I now have to integrate that over dx. All right, so I did the y integral from here to here, right? When I integrate up dy, I just get y. So that says x plus 2 minus x squared. All right, so there you go. Anyway, then now I have to do the x integral here, which is not bad, right? That just comes out to be x squared over 2 plus 2x minus x cubed over 3. All right, and that's evaluated between the limits of 2 and minus 1. Okay, and so anyway, stick that in, grind it out, and the answer comes out to be 9/2. All right, so there you go. I'm going to have to look at it a couple times before it really gets to sink in, but that's how it works. All right. So now let's just, like I said, let's just do it again. But I'll do it as a vertically simple, or whichever of the other one was, right? I'll do it in the other order, and I have to get the same answer, and I will. And this one, I think, it's a little bit harder. The one I'm about to do is a little bit harder than the one I just did, but they come out. All right. So anyway, let me just let's see. So. And then do I need to do that again? Probably. Okay. Oh, in fact, this is a little bit tricky too. All right, hang on. Let me focus on this a little bit. Actually, this is not a horizontally simple shape. Okay. However, it does break up into two that are. This is kind of what I was saying. So what I actually have to do here, I'm going to have to do this as two integrals. First, I'll integrate over y from 0 to 1 and take care of this piece. But then I'm going to have to do the rest of this, and the curves are different as I go across. Right here, I'm going from minus x squared to x squared, and up here I'll be going from a different one. But anyway, it then does, will come out to be the same. So I have to do this one first. So, let me just get it written up there. So I'll be integrating this at y from 0 to 1 here. And then my inner integral will be over x, and it will have to go from minus the square root of y to the square root of y, right? Because that's what, that's this distance that we're doing, okay? And so that's my first term, and I'll integrate it first with respect to x, then with respect to y, all right? Now I need the integral from over here. And so that's going to give me this term, so I will have plus, and now y will go from 1 to 4. All right, like that. And then again simultaneously, x then has to go from, if this is y is x plus 2, that's the same that x is y minus 2. So that's what I have here, from x is y minus 2, up to 2, because that's where it stops, right? And then this term here again is dx, and then dy. So that's I made that comment earlier that this is not vertically simple, but it can be broken up into two regions that are, and I can still do these integrals, and there's not much to it, right? So anyway, you do this integral, and I get y is 0 to 1 still, okay, and then the inner integral gives me 2 root y dy, and then this one over here again gives me still y goes from 1 to 4, like that, and then what I have here then is root y minus y plus 2, integrate that over dy, okay, and it's a little bit messier, but not too bad. I'll go ahead and write a couple more terms there. So this gives me 2, and then 2/3 y to the 3/2 power, because I'm just integrating that root function, and that goes from y equals 0 to 1, right? And then the next term then gives me plus 2/3 y to the 3/2. That's from integrating that square root there, minus y squared over 2, plus 2y, and that went from 4 to 1. Anyway, I think you can take it from there. And the answer comes out again to be 9/2. All right, so there's a couple of examples. You just got to get in there and get your hands dirty and figure out the steps yourself. Okay. Anyway, let me show you something else that can happen here. And this goes back to what I was saying about how the order can matter. So anyway, here's an integral, say that goes y 0 to 3, okay, and then x is y squared up to 9. I'll draw the picture here in a minute, you can see it. And then the function is y, this is one of the examples in the book, I don't remember which one, but it's from there. Okay, so anyway, there happens to be the integral. If you look at the geometry of this, it's just a sideways parabola. All right, like that. All right, and so there's my region there, right? This is the function x is y squared. Okay. Anyway, so what I'm doing here, if you look at this, this should have been, that's right. So I'm doing, I'm doing the outer integral first. So basically what I'm doing here is I'm integrating y from 0 to 3, and then I'm taking x to run from y squared to 9. So this has been set up as vertically simple, okay? But you look at that and see, and it should be clear to you that you can't do that integral, okay? So just notice this, the function, f of xy equal to y cosine squared of x does not have an antiderivative that you can write down. okay, with respect to x, that would be, right? So that means this picture would tell me that I'm supposed to do the inner integral first, but due to that cosine of x squared there, I can't. It's just one of those functions, like, kind of like e to the x squared, Gaussian function sort of thing. There simply is there is no function whose derivative with respect to x gives me that. So even though the shape is simple in this sense, I can't proceed from this point. I'm stuck. Okay, so anyway, but what I can do, the tricky part here, is I can reparameterize this in the other order, and then it will be possible. And in fact, it's easy to see, so let's just go ahead and write that down. So I just want to reverse the order, and so now my outer integral will be over x from 0 to 9, and then the x integral, the one inside there, is going to then will be y running from 0 to root x, and I still have my same function, but I'm setting it up in the opposite order. Well, the thing is, now it does have an ion derivative. And I'll do that. Let's just go ahead and get rid of it this way. So now, so let's go ahead and look at this. My inner integral, or my outer integral rather, is x is 0 to 9. And then I would have, say, the cosine of x squared going along for the ride. Like that. And then I've got the y going from 0 to root x of y dy, right? And then dx on the outside. Well, now I can do it, okay? Because this guy does have an antiderivative now, and in fact, it's just root x, or it's x rather when you write it out there. So basically, that integral is x up to a constant or something. Well, now, when I have x times cosine of x squared, I can do the integral, okay? I mean, I'm not going to, you can look at it later yourself, but anyway, so let me just make the comment this way. That now, after doing this integral, the one I'm left with does have an antiderivative, because the derivative of x squared is x. So in this particular case, it does. So by doing this integral in this order instead, I'm able to do it. All right, and so that really is a good example that shows how the difficulty can depend a lot on choices like that. All right? So anyway, that's a couple of, neither of those examples are trivial. The first one's not too hard, but you need to, so now it's your turn. You got to get in there and get your hands dirty. All right? Anyway, so I got a little bit more to say from 15.4, but I'm going to take another break, and I'll be back in a couple minutes.